Okay, so let's just get to this Reynolds thing quick and dirty, right? And it will still let us understand why. So one thing I can always challenge myself to do is to show everything is true based on the work energy theorem. You'll see me do this a lot, where I remember from physics 1 that I know change in kinetic energy must be equal to work done on the system. So the change in this kinetic energy, right, of thinking of it, the kinetic energy of this right here. I have to change this kinetic energy in this region right here, of going from 0 to here. So just in the calculation, think of this as going from 0 to here. What's the work done by these forces here? So that's 1/2 rho of volume, because it's 1/2 n, and then v squared. This is the difference from going from here to 0, so I'm just left with external squared. The second term is minus if I'm looking at difference. That has to be done by the work, and that is the work of viscous forces, because here are viscous forces. So that's sort of the rate, what is the frictional work done? So, and that would be times this distance. All right. So this is very rudimentary, and it's not even really that right, but you can see. So this row will stay the same. In terms of the volume, what volume I have? We'll have the length. Okay. I'll have the length. I'll have x value, delta value. And then for here, remember that right, we say that the viscosity is defined in this shear force, which is shear force that we can put in here. So I need to multiply this shear by an area, and we'll just turn this into a ratio. So this area, let's say it's L squared, or X squared. Okay, this length didn't matter. I lose a power here. I lose one there. Solve for this. Kill this 2 because you're just looking for proportionalities. So we'll go proportional here. And I'll have this. This moves over here if I multiply through here. And I have a rho left an x. Not quite a Reynolds number, but it's easy to rewrite it if you just factor out an x squared. So then you would get x, and that's the same as ta-da. So that's just sort of, you can just kind of see that this idea, this inertial term is coming from, right, that you're looking at how much energy has the viscous forces taken apart. So clearly that'd be representative about this inertial term, which comes from just this difference of kinetic energy. Just one way to get there. You can get here much more exact later, but as with all theory, you should be able to get to the same conclusion many different ways. And that's on track that you're right if you can. So what else do I have on this? So that's one thing is that when it comes to these drag forces, we actually have definitions for them in integral terms. So drag is some integral of the shear at the wall. And then we have a lift force, which is the pressure of a body over the surface. So really, instead of that, we're at the coefficient thing, what you're actually getting at is a shear coefficient from boundary layer theories to calculate this easily to then calculate the integral for the whole body, right? So the final thing I want to leave you with is this image of these lift and force drags. On some sort of body like this, there's a pressure distribution and there's a shear. So the shear, right, this is shear at the wall. Right? And then for pressure, you actually have this sort of, in the notes I have time to do this stuff better. Let's see. You'll see that this pressure, right? Pressure is all normal forces, right? And on this surface, for this whole surface, I have a normal vector and a tangent vector. So the idea is the viscous forces dominate this term right here. We'll do boundary layer analysis, and we'll get expressions for these coefficient of frictions to calculate this better. And then you actually can parameterize it and do an integral over an entire surface to get a total drag force. And then for lift, that's about pressure. And that is about, actually, since it's about normal, and you're dotting with a null vector, you can see how this pressure field affects based on curvatures in the body. So airfoils have this look because they're trying to get this situation where you have two up arrows to give you lift. So that's just my first motivation and introduction to this external flows and the goals that we have to analyze it. And I just want to reiterate, just like we calculated these Darcy friction factors, right, previously, we're going to do the exact same thing, only we're going to calculate CF sort of, right? So a coefficient of friction, and if you even have a laminar expression. And the turbulent one. So before we had little f's, now we have the coefficient of frictions, but it's always the same story. So before I leave, I think that was everything I wanted to cover. Yeah. So, right, the integral thing, right? Just maybe I said this. These things are important, right? Because when we wanted to talk about drag, right? So this as a vector, which is what you definitely care about, you have to integrate a pressure field dotted over an area, tangent vector over the surface, over an area, right? So there's two components to a total drag force vector, right? If you have some sort of body in this there, right, you can set up now coordinates where there'd be a net, right? You'll have a net lift axis and then a left drag axis. And you want them oriented like this because you really care about how much force is actually upward. But that's the idea, is these vectors right here are parameterized based on the object itself. So in a computer, you can actually calculate these things. So for the first part of this external, the hardest part is actually this part, which is called skin friction. Right? This other one, form drag. So most of the work will be here because, right, we'll do this analysis to calculate these coefficients, right? So we'll have that C of F is actually the shear at the wall divided by So getting this value makes this value easy. That can then be plugged into this integral, right? Let's say throughout a body, and you can calculate what this skin friction is. So understand that this skin friction term of drag is due to viscous force. Viscous forces meaning the friction of the fluid causes this. Form drag is different because you'll see this is the last week of the last part of these lectures just discusses the form drag. That is due to geometry. Right? This part right here is all due to curvature, right? And that's always the case. You see del dot n, right? Sort of term dot n. N talks about how right, as n moves along the surface, that talks about curvature. So this one can be, right, this one is easier to calculate only because you've designed the part, so you can actually parameterize these curvatures and these geometries. You can estimate here as much. It took a long time to figure out how important this other part of the summation for a total drag vector can be. And there are, right, and because again, right, you want to get the vector so you can calculate a power needed. If you way underestimate this value, right, if you just say it's all inviscid and say, right, whatever, hoonanny, I don't care, and don't consider any skin friction, you would be surprised how much power you would not, how much you would underestimate the engine that you would need to get through the air. And that challenged people a lot. I think Prandtl was one of the guys that came around to really hit this stuff on the nail through a very specific analysis that we'll get to calculate all these things. But in your head, it gets really confusing with this external stuff. In your head, just always tell yourself, right, just like you were calculating energies, right, the whole point of this section is this. You're trying to get this. Let's say I know that part. Your boss tells you the velocity, so it's all about what on earth is the total drag force. Before, we just used the curvature terms because it was easier. This idea of getting at how can I tell what this T at the wall, the shear at the wall is turns into a problem of how can I tell what this coefficient of friction is, and then that is what boundary layer analysis tells us. It tells us how to get this value, which tells us how to put shear, it tells us how to calculate force drag, tells you how to get power, tells you how much energy gosh darn engine needs. So I'm excited. Hope you are too.